Hello, welcome. This is a video dedicated to answering one of the bonus questions dedicated for assignment 2 provided by the course Linear Algebra Math 1600 Summer 2024 at University of Western Ontario. Hereby I grant the permission to my instructor to share the video with my classmates and post it in his office or on the door of his office. In this video, we will discuss how to find a vector that is not in the span in R4 and at the same time find a vector that is in the span of given vectors in R4. My name is Andy. This is the date, June the 16th, 2024. Let's go through some basic introduction. Given a set of vectors v1, v2, v3 in R4, each of the vectors will have 4 components. We aim to show that there exists at least one vector W such that W is not in the span. We'll also provide a method to find a vector that is in the span of U1, U2, and U3. Let's recall the definition of a span. Span of U1, U2, and U3 is the set of all the linear combination of U1, U2, and U3. In other words, mathematically speaking, we can say let any A1, A2, A3 belong to a real number. We can say A1, U1 plus A2, U2 plus A3, U3. The solution set of this equation will be the span of the given vectors. For A1 to A3 belong to R, it really means that they are just arbitrary numbers. For example, like A1 could be -1, A2 could be 9, A3 can be 18 if we really want to. And as mentioned before, the dimensionality of U1, U2, and U3, they are in R4, meaning that they are in 4-dimensional space. Each vector will have 4 coordinates or 4 components. So let's first find the vector that is not in the span. First, we will need to write the given vectors U1 to U3 as column vectors of a matrix A, right? And then we'll show that for some vectors W, there will exist an empty row such that we don't have any leading ones in that row to generate the corresponding component. By the definition of linear combination, if we cannot generate at least some components at that position, then we have found a vector that is not in the span. So here we choose that U1 is 1, 0, 0, 0. Transpose really means writing U1 in the form of a column vectors, and U2 is 0, 1, 0, 0, and as this will be the second column. U3 will be 0, 0, 1, 0. Here, this is in row reduced echelon form, meaning that for any arbitrary vectors W in R4, we can generate at least some components at the X position, some components at the Y position, and some components at the Z positions. However, for the last components, we have all zeros, meaning that we cannot generate any meaningful components at that position. This will say that if a given W has any numbers in its 4 components, then that vector will not be in the span. And here, as an easy example, we just make the last component 1, right? This is all zeros, and no matter what your A1, A2, A3 is, you cannot generate a 1 out of the linear combination of U1 to U3. Previously, we provided example with the unit vectors. This is a more systematic conclusion of what we just mentioned. In R4, we have E1, whose first component is a 1, E2, whose second component is a 1, E3, whose third component is a 1, and E4, whose last component is a 1. And you see previously, we don't even have R4, meaning that we lost the ability to generate any number at the fourth components. The general vector representation in R4, we have V1, V2, V3, and V4. By definition of linear combination, we can write them as V1 plus E1, which is this vector, V2 plus E2, and V all the way to V4 times E4. And it will look like this form. We can generate V1, V2, V3, and V4 in R4 space. You see, ultimately we need 4 unit vectors to generate the full span in R4. However, previously we were only given 3, so we will be missing 1 out of the given vectors. Let's say U1 is this guy, U2 is this, U3 is this one. We are still missing E4, the unit vectors whose fourth component is a leading 1. This is the example we just discussed together before. V equals to x times 1 plus y times unit vectors E2 plus z times unit vector E3 plus w times unit vectors V4. Now let's find a vector that is in the span of given vectors U1, U2, and U3 in R4. These are the concrete examples I came up with. They're just one example how you would find a vector that is in the span of given vectors. So you pick any arbitrary numbers for C1, C2, and C3, and then you calculate their scalar multiplication, and for each given vectors, and then you calculate the addition of so that you can find a concrete vector V. So for example, here we plug in the C1, C2, and C3 such that we can write out this equation, and then we'll compute the scalar multiplication first. -1 times 2 is -2. -1 times 0 gives us 0. -1 times 1 gives us -1. And -1 times 3 gives us -3. And following the same pattern, 2 times the column vectors U3 will yield this vector as well. So, and then we compute the sum of these column vectors, we'll find a vector V. That's an example of how to find a vector that is in the span of given vectors. So from the example above, we conclude that the vector V equals to -1, 4, 10, 5 is in the span of U1, U2, U3. And recall that U1, U2, and U3, they are the vectors we chose here above. So for given any vectors, you can follow the same pattern to find a vector that is in the span. This will demonstrate how any vector in the span of given vector in R4 can be found by choosing appropriate scalar coefficients and combining the vectors linearly. This is the conclusion we want to draw at the end of this video. Thank you. Hope you enjoy.